Hey everyone, and welcome back. Today, we're going to talk about the molecules that literally fuel our world and build so much of what's around us. This is the story of hydrocarbons, the fundamental building blocks for, well, almost everything. All right, let's kick things off with a little riddle. Take a look at natural gas, the gasoline you put in your car, and maybe even the plastic bottle you're drinking from. What on earth do they have in common? I mean, think about it. They're totally different, right? A gas, a liquid, and a solid. Well, the answer is actually incredibly simple. They are all made of hydrocarbons. And that's because these amazing, versatile molecules are the stars of our show today, connecting some of the most essential products in our modern lives. So, what exactly are these things, and how are they all related? Well, let's get to know them. We're going to break down this whole world of hydrocarbons into its three main families. Okay, first things first, let's get a clear definition. At the very core, hydrocarbons are exactly what they sound like. They're organic compounds made up of only carbon and hydrogen atoms. Seriously, that's it. Just two of the most abundant elements in the universe, but the ways they can link up are almost infinite. So how do we tell them apart? It all comes down to one thing: the type of bond holding the carbon atoms together. First up, you've got alkanes. They have single bonds. Think of them as the steady, reliable ones. They're very stable. Then we have alkenes, which have at least one double bond. This makes them unsaturated and way more reactive. And finally, you have alkynes with a triple bond. They're also unsaturated and whoa, are they reactive. This one little difference in bonding is the key to everything. Okay, let's start with the foundation of it all: the alkanes. You can really think of these guys as the stable backbone of the hydrocarbon world. They're the simple, sturdy building blocks in our molecular Lego set. So what's the deal with alkanes? It all comes back to those carbon-carbon single bonds. That simple structure is what makes them saturated, which is just a fancy way of saying they're packed full of as many hydrogen atoms as they can possibly hold. And because they're so stable, they got the nickname paraffins, which comes from Latin for little affinity. They just don't really like to react with other things. But what if you have one of those more reactive hydrocarbons and you want to turn it into a super stable alkane? Well, chemistry has a few tricks up its sleeve for that. One of the most popular methods is a process called hydrogenation. And this image shows it perfectly. You start with something like ethene, which has that reactive double bond. Then you add some hydrogen gas with a catalyst, like platinum or nickel. You see that double bond, it breaks open, the hydrogens jump on, and boom, you've transformed that reactive ethene into stable, saturated ethane. Okay, but what if you want to build a bigger alkane from smaller ones? There's another really clever trick for that. It's called the Wurtz reaction, and this one is super cool because it lets you literally double your carbon chain. So how does this magic work? You take two molecules, something like bromomethane, and you react them with sodium metal. Think of the sodium as being really aggressive. It comes in and just yanks those bromine atoms right off. That allows the two carbon-based pieces to snap together, fusing into one. You start with two one-carbon pieces and end up with a two-carbon alkane. Pretty neat, right? So we've established that the bonds are super important. But here's the thing: especially for alkanes, it's not just about the bonds. It's about the shape, the actual 3D structure of the molecule in space. You see, because alkanes have those single bonds, the atoms can spin around freely, kind of like beads on the string. This rotation creates different shapes, or conformations. On the left, you've got the eclipsed form. See how the hydrogens are all lined up? Imagine them bumping into each other. They don't like that. It creates tension, making it unstable. But on the right, you have this staggered form. Here, everyone has their own personal space. This is way more comfortable for the molecule, making it the low-energy, stable shape it prefers to be in. Okay, let's move on to the next family. If alkanes are our standard sturdy bricks, then alkenes are the specialty pieces. They're ready for action and way more versatile. And that reactivity is the whole reason they're the go-to molecule for making things like plastics, including that bottle we talked about at the start. So what's the secret sauce for alkenes? It's that carbon-carbon double bond. This makes them unsaturated, meaning they could hold more hydrogens if that extra bond were to break. But here's the crucial part. That double bond can't rotate. It acts like a brace, locking the molecule in place and leading to a totally new kind of structural puzzle. And this leads to something really cool called geometrical isomerism. Look at the cis isomer. See how the identical groups are on the same side of that rigid double bond? Now look at trans. They're on opposite sides. They're made of the exact same atoms, but this simple difference in their 3D arrangement can completely change how they behave, affecting things like their polarity and even their melting point. Okay, so that double bond is basically loaded with electrons, right? That makes it a huge magnet for other molecules. It's like it has a giant neon sign flashing, "React here!" And this brings us to the most important chemistry for alkenes, addition reactions, where we can add new atoms and build all sorts of new things. But that brings up a really interesting puzzle. Let's say you're adding something to an alkene that isn't perfectly symmetrical. Where does the new atom go? Does it attach to one side of the double bond or the other? Well, it turns out it's not random at all. There are rules to this chemical traffic. And the main rule of the road here is called Markovnikov's rule. It sounds a bit complicated, but the idea is actually pretty simple. It says that the other thing, the negative part you're adding, will almost always attach to the carbon atom in the double bond that already has fewer hydrogen atoms. It's a remarkably reliable rule. Let's look at a real example so this makes sense. If you add HBr to propene, that middle carbon has just one hydrogen, but the carbon on the end has two. And just like the rule says, that bromine atom goes right to the middle carbon. You end up with 2-bromopropane as your main product. The chemistry is so predictable. And get this whole reaction is actually a super simple and visual test you can do in a lab. Bromine water has this very distinct reddish-orange color. If you drip it into a mystery substance, and poof, the color vanishes instantly. You know you've got a double or triple bond in there. It's a classic test for unsaturation. All right, let's take a step back and look at the big picture here. We've seen how the type of carbon-carbon bond dictates everything: stability, shape, reactivity. Let's wrap up by looking at why this one little detail matters so much and how it creates this insane variety of molecules all around us. So let's recap the whole story. Alkanes, with their single bonds, are the stable backbones. Alkenes, with their double bonds, are reactive hotspots perfect for building new things. And alkynes, with their triple bonds, are even more reactive. This is it. This is the key. That simple step up from single to double to triple bonds is what allows chemistry to build pretty much everything complex in our world. So I want to leave you with this one big idea to chew on. How can something so simple, the way two carbon atoms share their electrons, be the secret to building everything? From the fuel in our cars to the fabrics we wear, all the way to the DNA that makes you, you. It's an incredible look at how immense complexity can arise from the simplest of rules. Thanks for tuning in.